Hi, everyone. This is Hao Ran. I'm going to present a project that we collaborate with Wirong and Michiel on the topic of secondary succession patterns in tree size distribution along a rainfall gradient. We're using data from the second forward network, so huge thanks to them for providing that and awesome communication. We'll talk a bit about vital rates before jumping into the size distribution, which is the core response variable in this study. And then we'll jump back to vital rates and talk a little bit about the inverse problem. And the motivation behind the project is question, how do forest structure change with succession and rainfall? We want to be able to predict how size distribution change during succession under different rainfall regime. And the second forward data really allows this to happen. And the general idea is that environmental change during succession affect vital rates across species. And vital rates in turn affects the outcome size distribution. But we only observe size distribution and measure the underlying environment without vital rates. So we model the effects of environmental change on size distribution, but we'll build on some assumptions to implicitly account for the underlying relationship between vital rates and size distribution. And this is how it could happen. A lot of studies surrounding the metabolic scaling theory and invariant scaling of size distribution in tropical forests have come up with this framework. So if we start with the simplest growth size scaling relationship, which is a constant growth relationship irrespective of diameter, as well as a constant mortality across diameter, then if we also assume equilibrium, dynamic equilibrium, then the analytical outcome or size distribution should follow a negative exponential, which is like an exponential decay curve. When we relax the assumption of constant growth and assume a power law scaling between growth and diameter, then but keep mortality constant, then the outcome size distribution should follow a Weibull distribution. We can also further relax the constant mortality assumption and assume a power law scaling between mortality and diameter, in which case the power law exponent is negative. Then the outcome distribution can follow a power or a Weibull distribution depending on the ratio between growth and mortality rates. Basically, the general idea here is that rather than curve fitting your data, we can rely on simplistic underlying demographic assumptions and come up with a more mechanistically informed model to fit to data. And this is what we do. There are some studies that incorporated multiple distributions to account for multiple processes. Lai et al. In ICOS here, in collaboration with David Coombs, is a good example. They did a composite Pareto Weibull distribution. Basically, they have a threshold diameter and fitted Pareto to small stems and Weibull to larger stems to account for the different mortality processes in these two size components. We did a mixture rather than a composite distribution here. Mixture distribution is quite common in other fields, but not always in ecology. So why do we do a mixture rather than a composite? The simpler answer is that this is the only way. We know how to code in environmental effects. More on this later. But as we do that, we realize that this also relaxes the clear-cut boundary between understory versus overstory, because in a forest gap, the smaller stems in the so-called understory can also experience highlight. Taller stems can still be shaded by even taller stems. So we want to relax that and instead estimate the proportion of subpopulation coming from the so-called understory or overstory. And this is how it works under the hood. There is additional proportion parameter that estimate how much of your subpopulation comes from a Pareto versus a Weibull. There are 4 parameters in a mixture distribution, in our mixture distributions. The Pareto has an exponent parameter. The Weibull has a shape and a scale parameter, and then there is a mixing mixing proportion parameters that mixes the two. What we add here are the environmental covariates, forest age and rainfall. We allow them to moderate each of the distributional parameters. And then we also account for the interaction effect between forest and rainfall. So we hope to build a somewhat predictive model that predicts the observed distribution of diameter as a function of forest age and rainfall. We use the second forward data. As a first pass, we use a very strict selection criteria that still gives us a lot of stems across 36 clonal sequences and over 300 sites. It seems to cover a fairly good range of rainfall and forest age. So the data are preliminary. We want to take it as a grain of salt because we're still improving the model, which may change the effect size. But we want to show you the what we expect to show out of this model. Before that, we will look at some fits, the good fits and the bad fits. Each of the panels is a forest plot. The top panels are the good fit. Each panel is basically a probability density function overlay on histogram of diameter. In the insets, we have the log-log scale cumulative distribution function that most previous studies like to look at. So all good on the top, but the bottom, we see that even though sometimes the cumulative distribution functions show an acceptable fit, the probability density function, which the maximum likelihood algorithm is trying to maximize, reveal some overestimation or underestimation. Anyway, if we move on to the effects, here each panel is a parameter from the mixture distribution, and they are plotted against forest age, also affected by rainfall. We chose 3 rainfall regime here, 3000, 2000, and 1000. If we focus on the Pareto exponent, we see that overall it tends to increase with forest age, kind of converging to -2 as predicted by the metabolic scaling theory. And wetter sites also tend to have a less negative Pareto exponent, implying that they have slightly more larger stems than smaller stems. There is also interaction between rainfall and forest age, more apparent in the Weibull component. And the mixture weights also slightly change with forest age. In younger forest, mixture weights are the proportion of stem belonging to the Pareto or so-called understory subpopulation. So in younger forests, wetter site has a high proportion of understory subpopulation, but the opposite is found in older forests. So we don't want to overinterpret these results, but I just want to give you an overall general sense of what we hope to achieve out of this modeling practice. With a distribution, we can further look at various aspects of distribution. For example, the mean, variance, and skewness. If we look at the estimated mean diameter from the mixture distribution and plot that across forest age, we see an increase. And wetter site, the solid line, tends to increase more rapidly, and perhaps not very surprisingly. So this is just an example of what we can extract out of a distribution. Perhaps more useful is to scale diameter to crown area of biomass using some allometry equation. Because once you've done that, you can take the sum under the area of the distribution of biomass. Then you get a plot level sum that may allow you to look at or simulate change in biomass across successional age under different rainfall regime. Also, when you have that, you can look at the quantiles, etc., and maybe look at the year taken to reach a target size biomass distribution, like how long does it take for 10% of the population to reach more than 10 centimeter. And this can help guide management cycles, like logging practices, very similar to the questions asked in fishery. So now back to the vital rates. We've shown that you can use some simple underlying vital rates assumption to come up with the expected size distribution. For example, the Weibull distribution, the two parameters are direct functions of the underlying assumed mortality rate and power scaling between growth and size. So we wonder if one could flip the arrow to go from the distribution of parameters and inversely estimate the vital rates. And this can be very important because if we can do that, that means we can use snapshot data where the size distribution data comes from to infer vital rates that requires multiple years of measurement. And this may be very important to allow us to squeeze more data out of limited data set. And as we go, we thought of relaxing the assumption because in many data, including your data set, probably see that species vary in diameter growth, a diameter size relationship and mortality size relationship that varies across species. But we're not quite equipped with enough mathematics to do that. So we would really welcome help from or feedback from math-minded people. Please talk to us. And with that, I'll leave it with the final slides here. Thank you again for the Second Four Committee for arranging everything, data managers and field workers for making this possible. Thank you, Michiel, for answering questions for me. I'll see you guys around. Thank you.